So welcome to this session of ClimaCheck training. We are going to discuss how you interpret the data. This is absolutely the key point of measuring. We want to measure and analyze the data. So I will try to give you an introduction to measuring and getting the data to make sense to you. So, of course, the purpose of doing these analyses is there are two different aspects of it. One is the energy saving. I mean, we are wasting tremendous amount of energy in our industry today because the systems are not optimized. They don't run as they're intended to. So there are faults in the system, and there are lack of commissioning, and there is different components in the systems not matching each other as they should. So we see that there are savings between 10 and 40%, and this is all across our industry. There's any number of surveys showing very similar results. So very, very rarely there are systems working as intended. So we need to make a better job in the future. And of course, to measure is to know. So first step is to measure, and then it's to understand the measurements. So this is what I will try to give you an introduction to. So always consider that there can be something wrong with the measurement. Make sure that you don't waste time collecting a lot of data when there is a problem with your sensors, or you have missed to apply something correctly, or there is some misconnection, so you put one temperature sensor and plugged it in, and then by mistake it was not in the right contact. So always start with questioning your data. We try to put yellow on all inputs. So the yellow boxes, they are inputs, and check those so they make sense. We use PT1000 Class A, very high accuracy temperature sensors. And the range of most of the equipment we supply is -50 to 150 degrees. So if I make a short circuit in the sensor, it's going to show you -50. If I have broken the cable, so there is no contact, it's going to show you 150. So anything close to -50 or close to 150 should make you suspicious. We normally do not have temperatures that are -50 and 150 in the normal system. There are systems with very low and very high temperatures, and then we need to take into consideration that we might need to use special sensors. But -50 short circuit plus 150 open circuit. So check those. Then we have pressure sensors. These pressure sensors, most commonly supplied from us, is from 1 volt to 5 volt signal. So that means that if it's not connected, it's going to show you the offset of 1 volt. So a 10 bar sensor, we have a range of 10 bars from 1 to 5, so 4 bars for 4 volts span on the signal. So that means 1 volt will be -2.5. So when you have minus bars, you should normally be very cautious. The standard sensors are not good to measure negative pressures at all. We have special sensors for below atmospheric pressure. But regardless, be careful, make sure that you check your sensors. Best is to, before you apply a pressure sensor to the system, connect it to the equipment at atmospheric pressure, check that it reads atmospheric pressure plus minus a few kPa. So pressure sensors easy to check versus atmospheric. The big challenge, as always, is the power measurement. Make sure that you have a reasonable current on all three phases, reasonable voltage on all three phases, and that your power factor is correct on all three phases and the total power factor. So typically in larger compressors, we would want to have power factors near nominal loads, that is well above 0.9. Smaller compressors, it can go down to maybe even 0.6. But make sure that your power factor is consistent over all three phases and that it makes sense. Always check your max operating currents on your nameplate on the compressor. Make sure that it makes sense with what you're reading, so you haven't the wrong CT programmed or something. It's very frustrating to come back home with a measurement that is totally inconsistent on the power. So make sure you have it right from the beginning. So now we have checked all our sensors, we are getting reasonable values on all data points. So before I start looking closely, I check that I have subcool and in my system, because if I don't have subcool as expected on the type of system I'm working on, my refrigerant charge will be wrong. So then I of course better fix my refrigerant charge before I spend a lot of time on measuring. Again, same with superheat. Depending on what type of system I have, there is an expected superheat. And if I'm running with much higher superheat, there is an issue. And of course, my performance of the evaporator will be lousy if I have too high superheat. If I have too low superheat, I might even get liquid carryover to my compressor, and then nothing will turn out correct, and I might damage my compressor. So check your subcool superheat. Does it make sense? Is it what you expect? Before you start collecting real data. Of course, check that your compressor seems to be running okay. A good compressor today is running around 70% peak isentropic efficiency. So you should be around there if it's full load, good conditions. For a low temp compressor, you might go down to below 0.6. So at very high pressure ratio, you lose isentropic efficiency. But make sure that you are in the right neighborhood. If you are wrong, I mean, have you missed that you have some cooling on the compressor? If your compressor isentropic efficiency is 100% or 90% or 110%, you are cooling your compressor, or you have some input data that is wrong. There are no compressors above 0.8 in isentropic efficiency. So if you measure something higher, there is a problem. Find the problem, don't use the data. If there's any cooling of the compressor, you need to take that into account. So we can deal with cooling of compressors, but we need to deal with it, otherwise the results will be wrong. And then a traditional maintenance visit might have started with that the machine is not running. You're coming out for an air conditioning system, early spring, it's only 10 degrees outside, and there's no load. So then you would have started the chiller, but in reality you will not know if it works correctly, because it will just change the temperature too quickly. So you don't get any stable operation. Unless you have stable operation, you cannot check that your compressor is okay, you cannot check that your refrigerant charge is okay, you cannot check that your expansion valve works. So it's a meaningless test to run a compressor at continuous varying conditions. You need to plan to have reasonable stability of the load. And if you want to check your evaporator, condenser, compressor, and charge, if you don't know the system extremely well so you can judge based on part load, you normally need to have full load operation to be able to evaluate the system. So this, of course, needs some planning. It's of course attractive to go to sites and do maintenance checks when there is nothing else to do. So not during when there is a reasonable load, but the measurement is not going to be very good. So again, that's of course the big advantage with having continuous monitoring it. Then you just go in and pick out relevant data points. But try otherwise to measure at reasonable stability at as high load as possible. And if you have multi-circuit systems, it's best to measure them simultaneously. You can run one at a time and two at a time, and note in the protocol on the one that you are measuring that now I was measuring only circuit A. Then you note that now circuit B started, because of that will change the operating conditions for circuit A. And of course it's very interesting to know how they operate together, not only one by one. Many systems would have very small temperature differences on the water side if they run one circuit, and that will be a totally different operating condition than if you run both. So again, plan and try to get relevant data. And get stable data. To look at data when everything is changing is not going to help anything. Also, if you compare data with design or rating or something, always bear in mind what are the system boundaries that you are looking at. If you measure only the compressor power, then of course the performance is something different from if you include pumps and fans. And different standard for different type of units, they include some include fans, some include pumps, and some do not. So just don't compare without knowing what you're comparing. It can be apples and pears. So of course the best thing is to measure both compressor power and pumps and fans. Then you get the most complete picture, but all depends what you're measuring and what you're comparing with. And this is what we are doing when we optimize plants. It's so important because every degree we can increase our evaporation temperature is going to save between 2 and 5% of the energy and improve our capacity. The same if I decrease my condensing, it's 2 to 3% typically energy saving. So very often you can save 20% just by changing set points. It might not be possible to run at a lower pressure ratio all year round, but it's very rarely necessary to run at the maximum pressure ratio. And many systems, they have high set points on the warm side and low set points on the cold side, just to deal with worst case conditions. But that's very costly, and it increases the wear of the system. So always question if I can reduce the pressure ratio for the compressor and save a lot of energy. Then everybody will build their own method, experience on how they check through the data. Personally, I like to first focus, do I have the right refrigerant charge? Because otherwise everything will be incorrect anyhow. So then when I know that my charge seems to be okay, then I check my expansion valve. Then I check my compressor, then my condenser, then my evaporator. So I go through the same sequence every time because it saves me time. And I've found that this is the most time efficient way of looking at it, so I quickly catch where I have issues and can correct them before I continue the measurements. Then when I've checked my chiller, heat pump, refrigeration rack, then I look at what kind of conditions is it exposed to. What temperature levels, are the systems stable? Are the controls doing what they are supposed to? Does my capacity seem to match well the system, or is it going up and down in capacity all the time? And do I have any opportunities for heat recovery that they have not taken into account, or free cooling? It's strange when you're running an air conditioning system to produce 10-degree chilled water when it's 5 degrees outside, where you could actually cool with the outdoor air. We should not waste energy when we don't need to. Now we have checked that we have stability, we have good. Then I have the dashboard, which gives me all KPIs for the system, and it gives me a very quick overview of the system. I can see that this chiller, it's a low performing chiller. It's not terrible. It's working within what could be possible for some not highly rated chillers. So it maybe there would be significant savings, but it could also be a low cost chiller that the focus is low price. If I then start looking, okay, I'm not so much focus on the refrigeration process, then the compressor efficiency. Here I immediately see that this compressor is running at very low efficiency. So this is then of course the reason to my lower efficiency is that my compressor is either it's worn down or it can be part load, but it's running terrible. So it's not going to be what I desired of the system. So that's for clear. So I can, of course, look at the data in the pressure enthalpy chart, but actually this is mainly good for my understanding of the process, especially if I have more complex processes. It's good visualization of how any process works, but of course the only thing that gives me a visual impression is the superheat and the subcool here, which are data that I already have in the KPIs that we are showing. But this shows me, of course, that I'm using this to get my performance of the system. The COP is the cooling capacity divided by the electrical power. So we have our enthalpies and we have our heat losses that we take into account. But then we get the COP for the system in a totally scientifically unbiased way. Doesn't include any data from compressor manufacturer or chiller manufacturer. We get the same data regardless of what brand or type of system it is. So then if I go down to my cold side and look, we are measuring our chilled water or air temperatures, inlet and outlet. We are measuring our evaporation pressure, and we are measuring the temperature on the inlet. If I have long suction lines, I can add a sensor to measure the evaporator outlet, because that is typically what the expansion device is sensing if I'm using a electronic or thermostatic expansion device. So if the suction line is long, it could have significant pressure drops and so on. But if I measure the superheat at the compressor, which I need to evaluate my compressor, then of course I can judge if the additional superheat from the suction line makes sense to what the expansion valve is controlling. So I look at my approach, which is the difference between the outlet chilled water for a water cooled and the inlet air to the evaporation. So I compare if the performance of the unit. I can look at my delta T's to see if I have reasonable flows. We can, when we have the cooling capacity, we of course also know the flow of the air or water. So we have all the data we need to evaluate the evaporator. Of course, one challenge is that still it's very rare that there are relevant data in the operating manuals. So if you haven't measured on this system or a similar system before, it's easy to say that this is high efficiency, it's low efficiency. The expansion valve is working very efficiently, or it's working less efficiently. So you can always correlate it to good practice. But of course you don't know if somebody bought a cheap evaporator or if it was a good evaporator that has deteriorated. So to have design data is always very helpful to be able to be very specific when you do the evaluation. So there is also a lot of this, if it makes sense. I mean, I cannot have a colder chilled water going out than evaporation. So the evaporation always has to be the coldest temperature. So these are kind of just to bear in mind that we know where the system should be. We cannot get the suction gas coming out of the evaporator to be warmer than the incoming air or incoming water. So we have these rules on how the system should behave. So always take a look at the data to make sure it makes sense. So all the sensors are the same, all the sensors are correctly applied. Then if I have my superheat not looking correct, always before you spend time on evaluation, check that your subcooling is okay. If you don't have proper subcooling all the way to your expansion device, it's going to be very difficult to get it to work correctly. So, of course, it can be a question of that there is a shortage of refrigerant, but it can also be a pressure drop in your filter dryer. There can be a solenoid valve before the expansion valve that's not working correctly. There can be a blocked strainer. Can be many reasons why your superheat is increasing. That is not the expansion valve itself. It's that it doesn't get the chance to run properly. Of course, if the pressure ratio is too low for the design of the expansion device, the superheat will also increase. Also, unstable expansion valves are quite common, and in many cases they might not have been checked for proper operation over the whole envelope. We are going to have the biggest risk of hunting of the expansion valve when we have a very high pressure ratio and low capacity. So if I have tandem compressors or variable speed compressors or different type of capacity change of our compressors, when I run at minimum capacity with maximum pressure ratio, that is when I'm going to have most challenges with getting a stable expansion device. So always good if you can check at maximum. Then, of course, the other end of the envelope for the expansion device is when you have minimum pressure ratio and maximum capacity. Then you're going to have difficulties in getting enough refrigerant through. So that is the other end that you need to check. And the superheat will, in most cases, be higher at minimum pressure ratio, maximum capacity than what it is at maximum pressure ratio and minimum capacity. So a good operating manual for a chiller heat pump should specify what the minimum superheat should be and what the maximum superheat should be, as well as the minimum subcool and maximum subcool. Yes. So don't adjust your expansion valve before you have seen that it has proper operating conditions. If you change the expansion valve on a system that has low charge, creating some flash gas to the expansion valve, you are in a risk of that when somebody later come and recharge the system to correct charge, your valve is too open. So we come to the subcooling. Same drill. We check that the superheat is okay, because of if I have too high superheat, there is less refrigerant in my evaporator, so that will be high superheat will give you high subcooling. So I need to look at these together. They need to balance each other. Again, capacity. If I have low capacity operating, my subcool will decrease in most systems. So look at your system. Preferably you have recommendations for what it should be. If there is a prior ClimaCheck measurement, then you have it all documented there. So try to build experience. Try to make sure that there are available information on each site. So next person who is evaluating don't need to reinvent the wheel. There is one thing that we see frequently when there are a receiver in the system. People think that there should be subcool, but there can be no subcool after a receiver where you have both vapor and liquid. So if you measure pressure at the compressor and temperature at the liquid line, what you're actually measuring is the pressure drop between the pressure sensor connection and where you put your temperature sensor. If you have two-phase refrigerant, you are going to have zero subcool. And this makes a problem if you put your expansion device very near after a receiver, because you have no subcool out of the receiver. Then you normally have a filter dryer, many times in a solenoid valve, you have some tubes and so on. So you're going to have flash gas to the expansion valve. So that is, it's not easy to get the system to operate with a refrigerant receiver close to your expansion device if you have no subcooler in between. This is just a terrible case that I saw when I was driving here in Stockholm some time ago. This is it's 18 degrees outside, so it's not very warm, and they have put a condenser destroyer in front of the condenser to keep the condensing down. And you can see how the water is pouring all the way down the street, and you're destroying your condenser that was not functioning well from the beginning. This is absolutely not acceptable. There is no system designed for having a water sprinkler required when it's 18 degrees outside. And if your system is not designed to operate at the conditions you're operating, you should question it rather than trying to fix the system short term with a water sprinkler. This is going to put a lot of fouling on your condenser, so it's quickly going to deteriorate, but it also costs a fortune in water consumption. So not a good solution. Fix the problem instead. So if we look at our subcool and our superheat that I've been discussing, these will always respond to each other. I have a specific internal volume of my system, and the superheat requires space in my evaporator. If I increase my superheat, it requires more space in my evaporator. So that liquid refrigerant that is then not in the evaporator, it has to go somewhere else. So it goes to the condenser. Again, if I have a receiver, that will be the buffer. But typically, in most systems, if you can avoid a receiver and instead have a bigger condenser, you have useful surface in the condenser, improving your performance, which is much more cost effective than the receiver. So there are, of course, systems where you have a large number of evaporators that can be turned off totally. You have to be able to buffer more than what you can do in your condenser. So in direct evaporation systems, a refrigerant receiver might be required. But many times you see receivers that are extremely not cost effective, because it would have been cheaper to add volume to your condenser, just a bigger condenser, which would be useful surface and not requiring the safety valve. And many times receivers have sight glasses that increases leakage risks and so on. But in principle, you will, if you increase your superheat, you move refrigerant to your condenser side, which will increase the subcool. So these interact, which is important to understand, because of if you get flash gas as the subcool is not sufficient at the dips, it's going to interfere with your expansion device. So you need to, even at the minimum subcool, have sufficient liquid to give the expansion valve a reasonable chance to operate well. So, I mean, if we think about the evaporator and condenser as two vessels that are fixed volume, it's easy to understand that when I change my operating conditions, the liquid and vapor need to be somewhere, and I can intuitively understand what's going to happen when I change my operating conditions. So just to repeat, if I get more liquid in my condenser, that gives me more subcool, and I need to always make sure that I have solid liquid from liquid to my expansion device. Otherwise, it's trying to pull through vapor, which requires much higher velocity to get the same mass flow through. So as soon as I get vapor to the inlet of the expansion device, it tends to be insufficient in size to handle it. So then we come to our compressor. Now we have checked our heat exchanger, our refrigerant charger, our expansion device. We have good operating conditions for our compressor. So we measure the pressure and temperatures on the inlet and at the outlet, and we measure the active power. So these data we can put into any compressor design software, and we can get and compare the data with those. And experience showed that they compare very well. I mean, there is not a lot of individual variation between the compressors supplied today. They are very, very consistent. So when you measure, you can just enter your inlet conditions and your outlet condensing pressure, and the software will give you the performance that is expected. So here it's just one example showing the compressor efficiency being just slightly below the design isentropic efficiency at identical conditions. So this compressor is just slightly below the new compressor, but absolutely not seriously. So it's very easy to check that your compressor performance match design for all those compressors that are available as service compressors. I mean, Copeland, Danfoss, Spitzer, Frascald, and many others have softwares available on the internet. This is an example of a very unstable system. It's operating with unstable evaporation continuously, and we can see how everything is varying, including the compressor efficiency. This increases the wear of the compressor drastically, and this was not corrected, so it didn't take very long before you can see here how the compressor that was running in 55-60% efficiency, then suddenly here it drops to below 50 with severe damage to the compressor. These continuous variations are not good for the reliability of compressors. So compressor efficiencies, the peak performance is fairly close to most compressors today. They are 70, 72, 73 maybe for the best. So peak performance around 70 is very, very common. But then they, of course, lose efficiency when you remove yourself or remove the operating conditions from the design conditions. And in general, you can say that screw compressors and scroll compressors, they're built for a certain pressure ratio. So they are more sensitive for being off-peak design, whereas a piston compressor tend to have a higher likelihood of having a flat isentropic efficiency curve, because of when the pressure inside the cylinder reach the pressure on the outside, the valves open, whereas screw or scroll tend to over compress or under compress if you're not at the peak. So best case is, of course, to compare with design of the compressor when you have those available. If you don't have them available, you can say that if compressor isentropic efficiency is below 55, you are getting very, very low. If it's a low temp compressor at maximum pressure ratio, it might not do any better than that. But if it's an air conditioning heat pump compressor at reasonable pressure ratio, you should be well above 60 over the whole envelope. So these are just some rules of thumb if you don't have access to your to compressor softwares. So, I mean, we can check everything when we have done our measurements. So we can check the design of I mean, if we're measuring when it's very hot outside or cold outside, we can even check the design of the building and if the chilled water temperatures are correct, if the cooling water temperatures are correct. So we get an overall picture of the whole system. And then we can drill it down to each chiller or heat pump or whatever it is we are measuring to compare how it's performing. So if we have good data for the design, it's very easy. We just check that it's according to the design. And recently, International Energy Agency, they published a guide or published guidelines for measuring and verification of ground source heat pumps. And in their vocabulary, heat pumps is also refrigeration and air conditioning. You are pumping energy, so you call it a heat pump, regardless of the application. And the focus was on ground source because of that. Those are very high investment. So there is a special interest when people do a high investment to verify and benchmark the systems. But in practice, those guidelines in Annex 52 from the International Energy Agency, they are extremely useful for any measuring and verification in refrigeration, air conditioning, heat pump systems. It doesn't make us any difference if we are taking the heat from the air or from the ground. The principles are the same and the measurements we need to do are the same. This is one example of how Carrier use ClimaCheck to validate that the supplied unit is operating according to a specification. So this is a 38HXC chiller heat pump, and they first measure it, but you can see that they could not measure it at the nominal data. They had different temperatures that it was operating at. So then they take and enter the measured temperatures into their design data software. So then they can see that, yes, the chiller is performing extremely close to the design. So they can document that it is well within specification. Then we come to the interesting part of that the chiller and heat pumps, they are not, in most cases, working at the absolutely best. But the most problem is not because of problems in the chillers or heat pumps or refrigeration racks. It's because of that the conditions are not as they should. So we see a huge number of systems where there is way too many starts and stops. We see many systems, with fixed chill water temperatures that are absolutely not necessary. Air-cooled chillers, most of the case, the controls are left on some kind of default setting between 35 and 40 degrees condensing, which makes no sense because of most of these air-cooled chillers, they will work well down to, depending on the compressors, but we see that many work well below 30, some 32, but you can get them the minimum allowed condensing pressure for the compressors. And of course, you should not force up the condensing because it will cost you more in compressor wear than in fan power on almost any system. It's extremely rare. I don't know if I've seen a case where you save money on the fans more than what you spend on your compressors when we are talking about this type of high set points for condenser fans. And then next case, of course, when you have fluctuation in capacity and so on, what is triggering this? It could be a three-way valve on an air handling unit that is sending pulses on your chilled water, causing the pressure to the capacity to go up and down. But we see that even without any changes on the return water, we see many chillers that at certain capacities, they cannot handle the controls. So you need to check that your controller can handle your system. We have a lot of water in most chilled water circuits, most heat pump circuits. So you have a lot of inertia in your system, and you need to use that. You don't want your capacity to respond instantaneously to any change. You want to have a slow response to allow your system to slowly move to the right temperatures, not quick changes, because of then you will get pulsations in your system and you will have a lot of starts and stops. So here's an example from an IKEA store here in Sweden. So during daytime, it's operating reasonable. You can see that it's triggering, the yellow here is the power. You can see that it's very short spikes, and here you have spikes and drops in a short period of time. So you can see that it's sensitive, but it doesn't cause drastic problems in the day. But then when they shut down the ventilation at night, the capacity decreases. Then the controller cannot handle this. It's cycling on the 10 minutes restart delay. So it does not allow system to start more than until it had been 10 minutes since last start. But so it starts 1 minute, and of course during that minute there is no changes on the return of the water, but it still shuts off because the supply water decreased. Then it cycles like that. And this breaks the screw compressor, and it costs maybe 25,000 euro to repair it. So it becomes extremely costly that nobody checked the system during nighttime operation. Of course, there was no technicians at that time, but if you log a system, it's very easy to see that it's unacceptable and that you need to address the problem. This is a really fantastic compressor. We have over 100% isentropic efficiency of the compressor. Of course we do not. So I don't want to hear about these compressors, because anybody can understand that we don't have compressors. I've told you that they are never more than 75%. And then if we have 100%, we are doing something wrong. And if I look at this, I can see that I have negative superheat. So this is 407C, where we can actually have negative superheat. So we are feeding liquid refrigerant into the compressor. We are getting a very low discharge temperature for the evaporation pressure and condensing temperature that we are operating between. So we are cooling the compressor with liquid refrigerant. And this had been this is a heat pump where they have had a lot of problems. And when I started to investigate the history of this case, it turned out that they had problem with the terrible performance of the evaporator. So somebody who came out, they figured, oh, I have too low evaporation, and have learned somewhere that if I decrease my superheat, I'm going to get better performance in my evaporator. So they decreased the superheat, and when they did this, the refrigerant charge was low. So they didn't. The consequence was that the expansion valve was totally open, and then when they fixed the charge, the next technician that was there, he fixed the charge. Then it was flooding, and the problem here was that they had fouling in the evaporator, which should have been fixed from the beginning. That had saved them a lot of cost and a lot of concern from the customer that didn't dare to leave his house when it was cold outside because it was dripping so much. So the foul evaporator must be fixed before they can get the system to work well, also in this case. So when you have the performance of your heat exchangers, it's easy to address the problem. Here is just another comparison where the data points is taken from the measurement, enter into Copeland's compressor software, and showing that the system is behaving extremely close to the measured data. So that was the last picture for today, and I hope you picked up some useful tips on how things work. Thank you very much.